Take your attendance. Okay, sorry. Okay, let's start today's lesson. Okay. So, okay, where we are, what we did last class. Okay, let's recap first. Okay, first of all, can you hear me, right? Anybody? Can you hear me?
Yeah.
Okay. Okay, thanks. Okay, so gravitation. Okay, let's explore further. We've done about Newton's law, gmm/r squared. Then we explore what is meant by gravitational field strength, the gm/r squared gravitational field strength. Then we check how the field pattern looks like. Then how the gravity change center to the surface, and what are the factors effects, mainly the rotation. Then we explored finally how to launch a satellite, and we discovered that Newton's law of gravitation help us to get the height to be launched by using this equation. Gm/r squared equals to centripetal force. So we can find the omega substitute with 2 pi over t. You can work out this equation. Okay. Okay, so I go to the PowerPoint. Okay, explaining further. Okay, this is you have 2 PowerPoints for gravity. Okay, this is second slide. Okay, you can check from the times. So this is a part 2. Okay, second slide, we're going to talk about gravitational potential energy. But before we talk about this, we talk about the satellite first. But the satellite part is towards the end. So I scroll back. Okay, scroll back, skip this gravitational potential. Yeah, period radius from here. Okay. Okay, from the second PowerPoint, I think the towards the end you have few slides which talking about satellite. Okay. Okay, so I believe you're familiar with these equations. Okay, just now we derived, right? Okay, so how to get the orbital speed? The t squared is found to be proportional to the r cube. Okay, this is a universal equation again. It's not only applicable for Earth and satellite, it's applicable for all the planets. Okay, so Sun and Earth, this formula apply. Okay, Earth and Moon, this formula apply. But in this formula you have mass. This mass, remember, this mass is mass of the center planet. Okay, for example, if you considering Earth and Moon, this mass should be which mass? Should be mass of the Earth, the center planet. If Sun and Earth, if this equation used for the Sun and Earth, the mass must be the Sun mass. Remember. Okay. Okay, we successfully find what is the height to be launched. Now we're going to talk about, so yeah, t squared proportional to r cube. Kepler, this one scientist who we make use of the Newton's law to describe this further. Okay, this all the t squared r cube has been proved for different planets. Earth and Mars found to be as the same constant for t squared over r cube. This confirms the idea of Newton is correct. Okay, now we talk about, as I told you last class, the last part of the lesson, I told you, it's not necessary height is enough. What speed to launch? Orbital speed. So how to get the orbital speed? So satellite body is a body that orbits around another body. So you know that it's moon revolving around the Earth. It's a natural satellite for Earth, and man-made artificial satellites navigating surrounding Earth. More than 1,000 over. We have satellites. Okay, launching a satellite. So like firing a bullet from a cannon. You see this picture. If you launch quite a low speed, you're going to fall to the Earth. You increase the speed, you're going to fall to B, further distance. But if you increase a very high speed, it might rotate in a nice circular path. Okay, so that's called orbital speed. To set a satellite in orbit, it is first carried out in required distance from the Earth. Then the satellite is launched at a direction parallel to the Earth's surface, defined velocity. Okay. If the satellite is launched with a velocity which is less than the required value, what will happen? It will crush to the Earth, right? Like what is happening every day. You're throwing a ball horizontally, you're going to crush to Earth. You're going to fall back to the Earth because the speed you launch is very low. Okay. If you go higher than that, it's going to subsequently leave the orbit. Okay. Okay. Now, what speed required to launch the satellite? How much speed to give a satellite so that orbit in a circular path? Again, the equation to be equated is the gravitational force between the satellite and the Earth must be equal to the centripetal force of the satellite. Okay. In this case, we use mv squared over r because we want to get the orbital speed v instead of mr omega squared because they don't have orbital speed. So we put the v here. So mv squared over r to be used. So you equate, you get the orbital speed. This is the speed, orbital speed required for the satellite to sustain in the circular path. Again, what? Gravitational force balanced with the centripetal force, you get the orbital speed. Same like the period formula just now. Okay. The period formula also, gravitation force equals to the centripetal force, but we use mr omega squared so that we substitute the omega halfway in terms of period, we get the formula. Okay. So both gravitation equate with centripetal force. Okay. So root of gm over r. So satellite, so scientists said, okay, we know what height to launch. So if you know the height above, okay, the r, if you know the r from the first equation, the t squared equation, you substitute the r in, what mass here will be? What mass is left here? This is which mass? Mass of the Earth or mass of the satellite? If only one mass left, it's going to be the center planet, the center mass. So in this case, it's going to be the mass of the Earth. Okay, this is mass of the Earth. So mass of the Earth. So you place in, you get the orbital speed. Okay. So yeah. So we go a little further about this equation. You tell me, so if you launch at a particular r to get a period of 24 hours, you get a certain orbital speed. Okay. Let's say from this equation, if a scientist, if an engineer, let's say a country launch another satellite which is lower than the what do you call the actual distance. What I'm trying to say is, for example, let's say you have this Earth. Okay, let's say to launch a satellite for 24 hours. Let's say this is the r you calculated from t squared equals to 4 pi squared gm r cube. Okay, you put the t as 24 hours, change in 2 seconds, you get the r. So this is r. Okay, let's say, so the orbital speed you're going to possess how much? What speed need to be launched? The speed need to be launched is v equals to root of gm over r. R, this r and mass. Okay, now let's say the country want to launch a satellite quite near, shorter r. Okay, shorter r. In exam, they will ask if a satellite is launched at a shorter r. Okay, can you predict how its period going to be? How its orbital speed going to be? How its period going to be if you launch quite close to the Earth's surface, still out of space, Okay, all satellite have to be out of space, so that no drag force. Okay, so let's say this satellite is quite close to the Earth. compared to the 24 hours period satellite. If a satellite close to the Earth, how about the period and the orbital speed? Try to think with these equations. Tell me, what will happen to the period and orbital speed? Is it the period of this satellite going to be smaller than 24 hours or more than 24 hours? The further one has a period of 24 hours. Okay, the nearer one will have more or less. Daniel here. Daniel, what do you think?
Period will be more.
The period, do you think is going to be shorter or longer based on this formula?
Shorter.
Shorter, because smaller r will yield a smaller period. Okay, so remember, yes, we can launch a satellite quite close to the Earth. More closer the satellite launched, we will have a shorter period. Okay, we will have a shorter period. Instead, it go 24 hours, it might rotate the Earth maybe in 12 hours. More closer, more shorter the period. Okay, remember, put in your notes. Okay, more closer the satellite, more shorter the period. What is the supporting equation? T squared equals to 4 pi squared gm multiplied by r cube on this equation. So you can say T squared proportional to r cube. So when r reduces, the period of the satellite reduces. Okay, this not only works for Earth and the satellite. It works for our planetary system, Sun, and other planets. You see, our Earth is the third one, right? Third, and you got a Jupiter. Okay, more further the planet, because these planets all are like a satellite for the sun, like going around, right? So tell me, Earth has a period of how much to go around the sun? It says 1 year. Predict for me. How about the Jupiter? Jupiter has a period will greater or smaller than 1 year? Still, this formula applies. This formula applies. Greater the r, greater the period. So more further the planet, more greater the time it takes to go one round around the sun based on this equation. Okay, T squared proportional to r cube. Okay, so closer the satellite, smaller the period. Okay, if the satellite is closer, what is the orbital speed it going to be? It's going to orbit, you need to be orbited or you need to be launched faster than the further one or slower than the further, based on this equation. Brendan here, what do you think, Brendan? Brendan?
Slower.
Slower from this equation. V equals to root of gm over r. More smaller the r, and r gets smaller. What happened to the orbital speed? Increases, right? Because inversely proportional, increases. Okay, so if any satellite launch close to the Earth, the orbital speed going to be very high. Okay, the orbital speed going to be very high. So in reality, we can launch any satellite any height you like. Actually, in reality, you can launch satellite any height you like. The only thing is our preferences. Our preference is we want to get 24 hours. That's why we go for. We have no choice. We have to go for the specific R. You want to have a satellite less than 24 to 12 hours, you can. You launch lower, you launch it fast, so we're going to move fast with a lower period. But we got one problem with this satellite. We cannot have a continuous communication with this 12-hour satellite, because when we go one round, the satellite already move ahead from that country. It won't be always on top of that country, because the period is not 24 hours. So we lose communication with the satellite. We only get communication with the satellite maybe after maybe 2 days later, because when we come back again on top of the country, we can communicate it back. So that's one problem. Okay. So what my point here explaining here is, you should know a satellite to launch, you need to have a specific period, a specific R, and specific orbital speed. More closer the satellite, more smaller the period, more faster the, more greater the orbital speed. Okay. Any questions, guys, from what I'm trying to tell you? Okay, okay, good. So no questions. Go back to the. Okay. So this is the equation. Okay. So now go to the next one. So one example. Calculate the speed of satellite orbiting the Earth at a height of 2,000 kilometer, 30,000 kilometer. Two satellites been launched at different height. Okay, Earth at a height of 2,000. This is height, height means latitude. Okay, so what is the orbital speed? Gm over r, root of Gm over r. R need to be the altitude plus with the radius of the Earth. Don't forget, you get the orbital speed, 6,900 meter per second. Okay, at 30,000 kilometer, the orbital speed is 3,300 meter per second, just Gm over r. Okay. Remember, the r must be from the center to the center of the satellite. They purposely will give the altitude. We need to plus the radius of the Earth for the r. Okay. So here, very clear. More close to the satellite, more faster it travels. The orbital speed, 6,900. More further it is, smaller the speed. Okay. Okay. Any questions from this working? No questions? Okay. So let's go to the next one. Okay. For a satellite which is close to the Earth's surface, its radius of the orbit may be assumed to be equal to the Earth's radius. Estimate the speed. And this is for fun. Okay, let's say this actually never happens. You can't launch a satellite on the surface of the Earth, just above your ground. You want to launch a satellite. In reality, not possible. Why it's not possible? Anybody, why not possible to launch a satellite on the surface of the Earth? Because of air resistance. Because air resistance is going to slow it down, you're going to fall back. Another one is Earth was full of mountains, so you're going to block the movement. Okay, but this can be, you can launch a satellite at the surface of the Earth unless the Earth doesn't have an atmosphere, and Earth is like a perfect uniform sphere. Let's say it's uniform sphere, no hilly places, just a flat surface. Yes, then this is possible. Okay, just for fun, let's calculate. You want to launch a satellite at the surface of the Earth. What is the speed required? Okay, so the orbital speed is root of Gm over r. You put the radius of the Earth, and it's found to be 7,900 meter per second. Okay. Okay, maybe Superman can do it. Okay, but the planet must be no air resistance. It must be a uniform sphere. Then what will happen? What will happen? I tell you. That means what will happen is, clear this. That means on the Earth's surface. Okay, on the Earth's surface, if let's say maybe Superman can do it here. Let's say you throw at the Earth's surface with 7,900 meter per second. Okay, after a short while, we'll go and hit him from the back. Okay, you're going to move in one circle, 7,900 meter per second for our Earth. For our Earth. Okay, but of course the assumption is no air resistance, and second is Earth is perfect what do you call sphere. It must be perfect sphere. If these two conditions is obeyed, then 7,900 will get a satellite at the surface of the Earth, keep on rotating without fall to the Earth. Possible. Okay. So more closer the satellite, more faster the orbital speed. Okay, more greater the orbital speed, more shorter the period. Any questions? No questions. Okay. So let's see. So another one thing we're going to, you see, the speed required is 7,900. Let's see the period. The period of the satellite at the surface of the Earth. If you launch at the surface of the Earth, what is the period it could have? So we use period is 2 pi r over v, or we can use the t squared. Just now we derived. The t squared equals to 4 pi squared over gm times r cube also can. You get 5,100 seconds. Okay, I think about less than 2 hours. 2 hours, right? Less than 2 hours, it's going to hit from the back. You can go circulating the circle. This for unique for our planet. Okay. Okay, so we already talked about geostationary satellite. Okay, geostationary satellite. These are the pictures. We have geostationary satellite, got 3 features. Remember, okay, geostationary satellite is found above the same point on the Earth at all time. This is called geostationary satellite. It looks like always above the same country. It has 3 features. What is the 3 features it has? The first feature it has is it has a period of 24 hours. Okay, the first feature. Then second is where is the second? The geostationary satellite revolve around the Earth at the same time rate and rotation at the Earth about its axis. Next is the equator. Orbit Earth same direction of the rotation of the Earth. This is second. The direction of the rotation of the satellite is always the same direction of the Earth rotation, from west to east. Okay, the satellite always move from west to east. Earth moving from west to east, satellite also should launch west to east. Okay, so that follow the same country above. And the third, this is the second property of geostationary satellite. The third, the satellite is in the same plane as the equator. The satellite orbits above the equator. You see here, the satellite always above the equator. Okay, these are the 3 features. Remember, what is the feature of geostationary satellite? They'll ask in exam. First, as a period of 24 hours, move the same direction of the Earth rotation, west to east. Third, is orbiting above the equator. That's geostationary satellite. Okay. Okay. Geostationary satellite used for telecommunication. For example, for live telecast. Now we have Olympic in Japan. So all the events will be live telecasted. Will be sent to the other country by using a geostationary satellite. It captured the information. Okay, it sent the signal to another part of another satellite, and 3 satellites enough to communicate the entire world. So that satellite will broadcast to another part of the world. Okay, so geostationary satellite. But geostationary satellite in reality is very far away from the Earth, so it's poor. It has a very significant time delay. The geostationary satellite got a significant time delay. You can observe that when you watch when someone is interviewing somebody like in CNN. Okay, let's say of course the person interviewing maybe from different country. Okay, Japan and US, let's say. So there will be a certain time delay. You can see after the question has been asked, there will be a delay. The other guys will wait for a while before you're answering it, because there is a delay, because the signal have to go from the US to that satellite, go to another satellite, go to broadcast back to Japan. So come back again, so it takes longer time. Okay, few seconds delay. So if you go in your YouTube, you can see another type of satellite called polar orbit satellite. This is polar orbit satellite. Polar orbit satellite was launched quite close to the Earth, and it's circulating from the North Pole to South Pole. It has a period of 1.5 hours. Okay, this polar orbit satellite has a period of 1.5 hours. Okay, that means it was launched very close to the Earth's surface. Okay, the orbital speed going to be small or big compared to geostationary, the polar orbit. Its a period is very small. Period small, quite close. Period will be small. Orbital speed will be very high. Move very fast. The polar orbit. Okay. The purpose of polar orbit satellite is for GPS, for global positioning system. We use polar orbit satellite. Not one. Got many polar orbit satellites circulating now. Polar orbit satellite used for GPS, for weather forecast, because quite close to the cloud region. And why GPS? Because it's quite close, so the time delay is very small. Yeah, that's why we use polar orbit, and it move from north to south. This is extra information. What I'm telling you about polar orbit is extra information. You need to know in depth about geostationary. Any questions? No questions, eh? Okay, so this all are possible, all introduction of Newton's law of gravitation. F equals to gmm over r squared enable us to launch a satellite, which is helpful for a lot of things, telecommunications. Okay, so we have many satellites going around. Okay, all orbit satellites have the Earth at its center. Okay, so of course Malaysia already launched 3, Miasat 3A in June 2009, and we have few. Okay, yeah, so this is all about satellites. Okay. Okay, so that's about geostationary satellite in your word notes. So the 3 informations on top here, and this is the orbital speed. So here there is one question for you. You can give a try. Calculate the geostationary satellite, the distance, and the orbital speed required. Okay, so how are you going to work out this? What is the distance a satellite orbit center of the Earth need to be launched? A geostationary satellite. So what formula do you use? What formula do you use? T squared equals to pi squared gm r cube. Okay, you need to look, you're looking for R. Period, you put what? 24 hours in seconds. So 24 hours times 60 times 60. Okay. Then G, mass, you put mass of the Earth. Mass of the Earth is given. You get the R, 6.4.23 times 10 power 7. You'll get. Okay. And this value is from the center of the Earth to the point where you want to launch. This value. Okay. Then what is the orbital speed required? What speed the geostation is moving currently? So the formula is V equals to root of gm over r, as stated above here. Okay. So mass of the Earth, radius, the r you got just now, you key in. The speed is traveling now is 3075 meter per second. Okay, that's the speed of the satellite traveling, very fast. You change to kilometer per hour, is like 3075 times 3.6, around maybe around close to 10,000 kilometer per hour. Okay, very fast. The satellite's moving around. So all possible by using Newton's law of gravitation. Okay. Any questions so far? No questions. Oh, you got the idea? Okay. So that's about satellite. Okay. Okay, now we're done with the gravitational field, gmm over r squared. We done force between point masses, sorry, F equals gmm over r squared. Field at a point mass, the g, small g, gm over r squared. Okay. Excuse me. The field near the surface of the Earth, how g change, we done that. Then now we're going to do something a little tricky, gravitational potential. Okay, gravitational potential. Okay, this is the most trickiest part of gravity topic. So you have to stay focused. Okay, now what we're going to discuss is gravitational potential energy. Might sound familiar to you, right? GPE, what's big deal about that? Gravitational potential energy, you know before, right? What is gravitational potential energy for AS? What is the definition for gravitational potential energy? The amount of energy possessed by a body due to its position in gravitational field. That's gravitational potential energy, right? The amount of energy possessed by a body due to its position in the gravitational field. In the gravitational field. Okay. Okay, but what is GPE? Gravitational potential energy equation. What is GPE equation? MGH, right? MGH. Okay, so that's your AS. Okay, so AS syllabus, GPE, the energy possessed, the energy possessed by a body, due to the field. due to the field, due to the gravitational field. Okay. EP is mgh. Okay. Okay. This is the knowledge you learn from AS. Okay. Now this formula, there is some caveat. This formula only works for now it will be revealed to you. This mgh is only works if this is the Earth. It only works for a short distance. Only for a short distance. Maybe within maybe 2 kilometers. Within 2 kilometers, you rise the height an object for 2 kilometers away. I'm asking what is the potential energy possessed? You use mgh. Okay, it's about the same. Okay, we can accept it quite accurate, but this is only an approximation value. If you go like few kilometers away like a satellite, what is the potential energy possessed by the satellite use mgh is wrong. Okay, so now in A2 you will be introduced the original concept of gravitational potential energy, and a new potential energy will be introduced. This is not new for potential energy formula, you know. This is the original one. This is the original one. This is the original formula discovered by Newton. The mgh is just what do you call a small adjustment to this formula. That's it. Okay. So this is the original one. So I'm going to introduce you original definition and the potential energy in this topic. Okay, now whatever I'm going to teach you now, don't use it for AS. AS still this is your answer. GPE is energy possessed by a body due to its gravitational field. Okay, AS. Don't mix up the A2. A2 gravitational potential energy definition is different. Okay, that's what we're going to discuss now. Okay. So let's go to the next slide. Okay. So we're going to get what is meant by origin. What is the original gravitational potential energy definition? Okay, to understand that, you need to understand this slide. Work done. Okay, work done. Okay. You see, when we move a body of mass m from R, a body of mass m from R to infinite. R is from the surface. We move it to infinite. From R to infinite. What is the work done? What is the work you need to be done to bring a mass object m from R, from surface to infinite? What is work done? So the work done is this. Do you understand this integration format? If you, I believe all of you already learned integration and differentiation in your maths. Anybody? Do you learn integration and differentiation already in your maths? Do you learn integration, differentiation in your O levels?
Got.
Okay. Do you understand the work here? Okay. Do you understand this integration of R to infinite FDR? Okay. So what is this? What is this? How they got this? Okay, just a little clear this. See, just your maths. Your math. If this is y, this is x. This graph. Graph. You want to find area under the graph 0 to x1. How do you do? Through integration, right? You can integrate it, right? Integrate it, the limit of 0 to x1, so x1 to 0. What do you put? Y dx. This is the area of the graph, correct? This is your maybe your O level knowledge. This is your O level knowledge. Okay, recall back. Okay, integration. Okay, so one of the use of integration is what? Finding the area under the graph, right? Put the limit y dx. Okay. So now, if work, what is work? Work is the product of force times distance travel to the direction of the force. In other words, if I plot a graph force versus displacement as, okay, let's say the force changing like this, going up, coming down, going up. The area and the graph is the work. right? The area under the graph is work. Okay, let's say from 0 to x1, r, I put r lah, 0 to r. What is the work done to move from 0 to r? So how do you put in the integration format? So limit is what? 0 to s. This is y dx. Y is your y-axis. Dx is your x-axis. So here you put what? F and s. You put f ds, right? This is the work done in an integration form. Okay. So from what to what? Okay. Now, any questions, guys, from this, your O-level knowledge? Just I'm getting pulling from O-levels, how the integration format, the area. Calculate the area is the integration of the limit f ds. Okay, I hope you understand. Okay, we go up here. Okay, so now you see this format. The work done to bring from r to infinity, okay, is f dr. The force applied dr. Because if I plot the graph, how the graph going to look like? How the graph going to look like? If I plot f versus r for the planet of the Earth from the surface, the graph going down, right? Because the force is actually gmm over r squared, and the force drops. If you move from the r to infinite, the area under graph here is what? Integration of r to infinite f dr. That's what written here. Okay, r to infinite. So the f is what? Is gmm over r squared. F is gmm over r squared, right? Gmm r squared. So infinity to r. You integrate this. This you recall back your maths knowledge. How do you integrate this? R squared you bring up, become r negative 2 plus 1. You end up like this. From here to here, recall back your maths for integration. How do you integrate it? So it become negative gmm over r with infinite r. You put infinite inside minus the r, end up getting this formula. So physics, we're just focusing to this formula. The work done to bring from r to infinite is gmm over r. This is the work done. Okay, gmm over r. Okay. So why I'm telling this work? Why I'm telling this work? What is our core topic discussion here? We are talking about gravitational potential energy. Okay. So the gravitational potential energy, the new definition, I think the original one is related to this work actually. The work done from r to infinity is gmm over r. Okay. Okay, now I show you what is gravitational potential energy, the original definition. Okay, is this. Okay, this is the definition of gravitational potential. The original definition of gravitational potential. This definition don't ever explain in AS. Don't use for AS. This for A2 gravitational potential energy definition. A2 gravitational potential energy. It was defined as, okay, read here. The gravitational potential energy, the symbol is U. Last time we used EP, here the slide going to be U. U of a mass at a point is defined as, what is that? The work done on the mass in moving it from what? From infinity to that point. Work done from what? Work done to bring a mass object from infinity to that point. To that point, maybe to R from here. From infinity to that point. That is the potential here. It's actually the work done. Work done. Work done from R to infinite is how much? Work done from R to infinite. R to infinite work done is gmm over r. Okay. If work done from R to infinite is gmm over r, the work done from infinite to r, how much? Negative gmm over r. Negative work is done. Okay. You climb upstairs, you did a positive work. Okay. When you climb downstairs or you jump from a certain height, you did a negative work. Okay. Negative work means actually you not sweat. You won't sweat. You are not using your energy. The attractive force does work. The earth does work on you. So you did the negative work. Okay. Right. When you climb up, you sweat one. So you did a positive work. When you fall down, you did a negative work because you are not wasting your energy. The Earth pulls you down. Okay, so same thing here. When you want to move from the Earth's surface to infinity, you did a positive work, GMM or R, positive. But when you want to move from infinite to a certain position R, you did a negative work. So that is the definition of potential energy. So what is gravitational potential energy defined as? Is the work done on the mass in moving from infinity to that point. That's gravitational potential energy. The new formula is, not to say new, this is the original formula instead of MGH. MGH is just an approximation value. Original formula, original gravitational potential energy formula is negative GMMOR. Okay. In your O level, they ask what is the potential energy you possess now. You will say 0. Now you are sitting, you are having lesson. So what is the gravitational potential energy you possess? Based on AS, you say 0 because H is 0. Okay. But if they ask, if a university professor asks to the university students who are taking physics, what is the gravitational potential energy you possess now in the lecture hall? So the formula they must do negative GMMOR. This is actually the original formula to calculate gravitational potential energy. Okay, so negative GMMOR. That means what? Your gravitational potential energy you possess is positive or negative. Do you possess a positive potential energy now or negative potential energy now? You have a negative gravitational potential energy. Okay, you have a negative gravitational potential energy. Okay, so far any questions? Okay, so try to accept new definition for gravitational potential energy. Work done on the mass moving from infinity to that point. Okay, negative GMMOR. If you understand this, okay, let's try to get a better understanding. So this is the Earth. Okay, gravitational potential is negative GMMOR. Let's say you are at point A here, away from the Earth, point A. Okay, let's say gravitational potential energy you possess at point A, let's say negative 20,000 joule, let's say. Okay, what do you understand by this value? What do you understand by this value? What is meant by negative 20,000 joule? It's actually the work need to be done. It's the work done to bring you from infinity to that point. The work done to bring you from infinity to that point is the gravitational potential energy you possess. It's negative 20,000 joule. We calculate based on negative GMM over R. R calculated from the center to this point. Okay, now I want you, if you understand this term, you should answer this question. I choose another point, B, quite close to the Earth. Now you are at B now. Okay, so I want you to calculate what is gravitational potential energy at B. I give you two choices, negative 30,000 joule, negative 10,000 joule. Which makes logical based on the definition I show you. At B, which is quite close to the Earth, potential energy at A is negative 20,000 joule. Potential energy at B, quite close to the Earth, most probably have potential energy how much? Negative 30,000 or negative 10,000 joule. And I have a reason. I want the reason based on work done. Reasoning based on work done. Okay. Please WhatsApp me, anybody, all of you. What is the answer? Do you think it's a negative 30,000 joule or negative 10,000 joule? Okay. Okay, one of you said negative 30,000 joule. Okay, the others, try to think. Negative 30,000 or negative 10,000, which makes sense. Okay, one of you said negative 10,000. Okay, one give a reason. Very good. If you go to the work done, you'll get the answer. You need to understand the concept of work done. to what is potential energy at B? What is the definition? Is work done to bring from the mass object from infinity to that point. Okay. Yeah, majority said negative 30,000. Yes, correct. Should be negative 30,000. Right? Should be negative 30,000. Why it should be 30,000? Why should be magnitude? Why must be big? Because work done to bring from infinity to A is greater, or work done from infinity to B is greater. Which one is the work is greater? To work done to bring from infinity to B should be greater, right? In terms of magnitude. So magnitude must be big. So it should be 30,000 joule. It should involve big magnitude, 30,000 joule, because greater distance. But it's negative, negative because it's always negative. So the magnitude must be 30,000 joules. It should involve greater work, greater magnitude of work, because greater distance. Okay. Yes, good. So those understand negative 30,000 joule, you have that potential energy at B. Okay. So conclusion is, where do you attain the highest? Okay. Before I go to that, okay. So magnitude wise, when you get closer, the magnitude get big. When you get big, that means on the for the Earth, the potential energy at infinity will be how much? 0. Okay, potential energy at infinity will be 0. No work done, because work done from infinity to infinity is 0. No work done. When you get closer, the potential energy become more negative. It become more negative. At the surface, your potential energy at the surface is highly negative. Okay, you have a highly big negative potential energy. Okay, so in exam they will ask, where do you have greatest potential energy? What is the greatest potential energy you can attain? 0. Okay, the greatest potential energy a humankind, not only human, any object from the Earth can attain is 0 joule. This sounds funny, but this is the reality. The greatest potential energy you can attain is 0 joule. How much potential energy you attain now? Highly negative. Okay, like you see the B and A. B is negative 30,000. A is negative 20,000. When you go further away from the Earth, you get negative 10,000. You go to infinite, your potential energy becomes 0. So maximum potential energy you can attain is 0 joule. Okay, negative 10,000 big or 0 big? 0 is greater. In terms of value, 0 is greater. Yeah. So this is the new idea now. So any questions, guys, about potential energy? Your potential energy now in A2, all of us possess negative potential energy. Why the potential energy is negative? Because you are always trapped to the Earth. You are always attracted to the Earth. You are like a prisoner to the Earth. So you have a negative potential energy. Okay. You are unable to move away from the Earth. You always will be pulled back to the Earth. So you have a negative potential energy. Okay. So that's why it's negative. Okay. So what you need to remember is the definition of gravitational potential energy. What is the definition of gravitational potential energy? Go back to the slide. The gravitational potential energy is work done on the mass in moving it from infinity to that point. Okay. Any questions, guys? Any questions? Hope you understand. Okay, so I don't want to drag this further. We continue next class to understand it further about gravitational potential energy. So I stop here today. Okay. Yes, thanks.
Thank you, sir.
Thanks.
Thanks.
Thanks.